Okay, so in the last video, we were able to see or derive how these relationships hold, and our goal, remember, is to be able to estimate the bound for the remainder term of approximating an infinite sequence by a finite sum, right? So we are not yet there, but I just want to show you how to use this little inequality we have to solve just one problem in Stewart calculus text. So this is not yet bound, but kind of interesting to see how this relates to something already. So let me paste this. So it says use 4 to show that if Sn is the nth partial sum of the harmonic series, then this holds, right? This inequality holds. So the harmonic series diverges, but very slowly. Use part A to show that the sum of the first million terms is less than 15 and the sum of the first billion terms is less than 22. So for the first problem, I'll just get this inequality. This is what we need for part A. So what we have is, okay, from 2 to n, ak is less or equal to integral from 1 to n f of x dx. Now if you look, the only term missing in this sum is the first term. Otherwise we can call it Sn if we add the first term to this. So let me do that now. So if I add a1 to both sides to n, okay, I add a1 to both sides to graph from this, then this one goes into this and the sum will start from 1, and if the sum starts from 1, then this becomes exactly the sequence of partial sum, right? So this will be less than or equal to a1 plus to graph from 1 to n f of x dx. Okay, by the way, this example is an exercise in 11.3 of Stewart text. So from here, our AK, the harmonic series is this. This is the harmonic series, or since we are using K, you can call this K. So here AK is what? 1 over K. Now if you plug that in here, we would have Sn is less or equal to A1 is the first term of the series, so if you plug K to be 1, you get exactly 1. Then integral from 1 to n of 1 over x, replace K with x dx, right? So work this integral out. This is natural log of x evaluated from 1 to n, which is 1 plus, plug in n, you get natural log of n, then minus natural log of 1, which is 0. So that part is gone. And we have the inequality we are looking for, or have the inequality we asked to find. It's exactly the first part of this. So A is answered. Now let me drag this down and let's work on B. So B says the harmonic series diverges but very slowly. Use part A to show that the sum of the first million terms is less than 15. So let's see. The sum of the first million term is less than 15. B. We already have this inequality. So we just plug. Remember, n is the number of terms we are summing. So if we are summing the first million terms, is nothing but what? 10 to the 6th. That's million. So this is less or equal to 1 plus what? Natural log of 10 to the 6th. And this is equal to 1 plus, by properties of logarithm, or a property of logarithm, this is 6 ln of 10. And if you plug this into calculator, you get let's see, let me erase this. If you plug this into calculator, you get approximately 14.2. So what we now have is that s sub 10 to the 6th is less or equal to 14.2. And indeed, this is less than 15 as stated in the problem. Okay, now let's see the second part of B. It says the sum of the first billion terms is less than 22. So what does that mean? Billion term is 10 to what? To the 9. So by the formula, this, oops, I made a mistake here. So this thing should be less or equal to. It should be less or equal to. Okay. So this is 1 plus natural log of 10 to the 9, which is 1 plus 9 natural log of 10. So plug this into calculator, you get 21.72. So this means that we have the first billion terms is less or equal to 21.72. And indeed, you see that this is strictly less than 22, as stated in the problem. And this is enough reason to tell us that the harmonic series, this series, because you sum the first billion term and you just get 22, that tells us that the series goes slowly, even though we are told that it diverges, but it diverges very slowly, right? And someone begin to wonder whether the series actually converge, but it turns out that the harmonic series diverges. Okay,